Hi everyone, welcome to this continued video series on essential statistics, a primer module for data science and machine learning. We've been discussing on various topics belonging to basic statistical approaches for data science and machine learning. Most of the discussion that we have had were of foundational nature. We'll continue the discussion, and today we will talk about in this video central measures. In the previous couple of videos, we talked about population samples, data types, and data tables, and the overview. And in this particular one, I'll be talking about the central measures, or rather, centrality of the data. So, what do we mean by central measures? Is essentially as mean median mode is a very familiar term that uh, we have studied in school days or college days or even in our day-to-day work. And if you're associated with any kind of BI or data analytics, I'm sure you're familiar with these terms. Central measures play a significant role in statistical analysis, and it provides insight into the central tendencies of a data series in the dataset. And these measures generally are used to summarize and describe the typical and the central value within the distribution. So when we say distribution, it simply means a column or a data series. And that helps data scientists identify the central position or average value or average behavior of that particular data series. So mean, median, mode are the key central measures that highlight the typical or representative value in a distribution. So let's get started. So before we proceed, I just wanted to mention the examples here would be mostly conceptual. So I'll try to provide the example right in the slides. Python code is pretty simple. I mean, you have those things readily available in NumPy, SciPy, and Pandas. So what is central tendency? It refers to a measure that represents the central behavior or typical value in a data column. And that helps provide a single value around which most of the data tends to cluster. So what does it mean is, let's say we have a column of data and the central value, let's say this is the central value. The idea is the rest of the data or most of the data will center around this focal point or one typical value or one single value here. That's what it means by the central tendencies, and that makes it easier to understand general characteristics of the data column. Now in data science, why are we looking for central value in a data column? Essentially to validate whether we have the right data or not. And how do we validate? Comparing against our domain understanding or domain knowledge. So if we know that a particular column should exhibit a central value around 120, and if the data set has that indication, then more or less that means the data series is of good quality. So, what are the measures of central tendency? Mean, all of us know. The basic mean, I'll be covering some variations of mean, some other type of mean as well. So, the average value of a set of data points is mean. Median is the central value or 50th percentile value in a data column. It's like a middle of the series. We'll talk about when to use mean and when to use median. in our data science projects. Mode is the most frequently occurring value, mostly useful for categorical data, not for numerical data. So mode, let's say these are the values, and by looking at the series, you can see the value 7 and 8 are the most frequently occurring. So the mode would be represented as something like 7 and 8 or average 7.5. So this is mostly useful for variables which are nominal in nature. Let's say, so what are the examples of nominal? Let's say, vehicle type, sedan or SUV. So if you have a data set where you have a column vehicle type, and here you have sedan, SUV, MUV, and let's say you have 10,000 samples. In those 10,000 sample, whichever value occurs most frequently, that's the mode. Let's say SUV. Now, SUV is very popular nowadays world over. So most likely any automobiles data set will have SUV as the most occurring value. So that's called mode. And when do we use mode? It is useful to know, what's the most frequent value or in your data column, and if that matches your expectation, that means the data is of good quality. So median, what it is? It is a middle value of a variable. So let's say this is the series here. So before identifying the median, the values must be sorted to find out the middle one. And let's say this is the middle one. So the 4 will identify as a median value. So when we use this, median is calculated mostly for numerical value, like interval and ratio. We talked about those definitions. What is ratio? What is interval variable? And often this is also a very good indication of central tendency, especially when you have extreme values. Let's say, your values are 1, 2, 3, 4, 5, 99, and some values are 99999, something like this, and here is minus 1000. Those are extreme values. So if you do an average of this will give you a wrong picture of a typical value or central value. So whenever the data has extreme values, then we choose median as our measure. So median will give us the right reflection of the typical value. So continuing to mean, so this is all famous mean, taking the average of the data set or data series, which is represented like the values are added x1, x2, and xn, and we simply divide by number of samples. In the previous example, we talked about how the series can be affected by noise and outlier. So mean is very much affected by extreme values like noise or outliers. So if your data has outliers and you are not in a position to remove those because the other columns have associated columns are useful, then in that case we choose median as a measure. So mean is simply a central tendency that represents the average value of the set of numbers. It is calculated by simply adding them together and dividing by the number of samples that we have in the data set. So mean is just like mode and median, mean also provides the typical or average value in the data column. So mean or median, when do we choose which one? Median is less sensitive to outliers. And mean is very much sensitive to outliers. For example, let's say this is your data series, and the mean of this would be 270. Just because of one high value here, you have a very high mean. And then median here of the same four observations is simply the average of the middle value, which is like 30 and 40, and that's 35. That's better reflection of the general value in the series. So median is a useful measure when we have, very extreme or large values. So let's talk about some of the types of mean apart from the arithmetic mean or the average mean that we just spoke about. So arithmetic mean is like sum of the values divided by the number of samples. Geometric mean is a special one, and I'm going to define and describe with example what is geometric mean and when to use geometric mean in data science. Especially it is useful for data which is multiplicative in nature or exponential in nature. For example, compounded value or exponential attributes like birth rate, population growth, and for a study of bacteria and all those organisms, they grow exponentially. So in that case, arithmetic mean is not suitable. We have to use another measure, a variation of mean called geometric mean. Harmonic mean is reciprocal of arithmetic mean. It is useful for averaging the rates or ratios. So when you talk about ratios, then we use harmonic mean. We have another one, weighted mean, which means the data values coming from different sources have different weights. And applying the weights, and after that you simply do a arithmetic mean. That's called weighted mean. Truncated mean is when you remove certain portion of the values at the highest end and the lowest end. If you are not sure of the extreme values present in the dataset, you might want to just remove the top 1% and also the bottom 1%, and that's called truncated mean. Mid-range is like the average of the highest and the lowest values in the data, and it's a simpler mechanism, may not be very suitable. One more method is Winsorized mean. It is very similar to truncated mean with slight difference. And let's just wait for subsequent slides. I'll give you an example of these. The next two mean is not very typically used. It's mostly for physics and engineering field like quadratic and cubic mean. I just wanted to give you a display of what sort of means that we have in data science. In the next slide, I've highlighted which are the ones that are mostly, we see in the field of typical data science or machine learning, which is arithmetic mean, geometric mean, sometime, not always. Harmonic mean, not really so much. And weighted mean. Mid-range is kind of a weak mean, is really not very effective in situations, but it can be considered in some cases where you think the average of the lowest and the highest can represent the data. Winsorized mean is also useful, especially for data like income distribution. So let's just wait for the next slide where I'm going to show you the examples on Winsorized mean. Arithmetic mean we have covered, so let's look at geometric mean. So geometric mean is used to find central tendency of a set of values that are related to each other by a factor or by a factor of multiplication or exponentiation. So this is useful when dealing with quantities that change exponentially. So that means the values are multiplicative. And for example, something which grows and decays exponentially. In that case, we use geometric mean. So let's take some example of geometric mean. For example, compounding interest. Year one, the initial principal and then the interest rate. You apply it, you get the compounded value at the end of the year one. Year two is dependent on the year one compounded value, and then you multiply here. So compounding gives you an effect of exponential growth. Here, arithmetic mean will give you a wrong result. So we use another example is population growth. Let's say bacterial growth hour one is maybe this method is just a formula here, and hour two is dependent on hour one, hour three is dependent on hour two, and so on and so forth. So it's doubling in size every hour, so that's exponential growth. In this case also, when we take arithmetic mean, that would be a wrong projection. So the formula for geometric mean is quite easy. You take those values, multiply, and then this is the nth root. So basically you are applying the nth root means the number of factors that you have. So let's say 4 factors, so this will be a root of 4. That's how we compute the geometric mean. For x1, x2, x3, these are individual numbers in the data series. N is the total number of values in the set. So multiply all these numbers together and then take the nth root of the product, where n is the number of values. Quite simple. So this is geometric mean. So some key points about geometric mean. It is suitable for data when the values are ratios or growth rate or multiplicative or exponential growth or decay. And the data column should have non-negative values. It doesn't work with a data set which has zero or negative values because everything will become zero. It's sensitive also to very small value. So certain considerations that we have to make here before applying geometric mean. And use cases are mostly in the financial area, investment return, portfolio return, and you want to compute the average annual growth of populations or financial assets. The mean of these values that represent relative change to each other. In that case, we apply geometric mean. So how do we know the data is of exponential form? You can apply, visual inspection by doing some scatter plot or visual plots. You will know whether it is the data series is a good candidate for geometric mean. You can also try logarithmic transformation. Uh, if the transformed data appears linear, that means the original data was or is exponential. You can also examine the histogram. If you have like a long tail on one side, that means it is exponential in nature. You can also do QQ plot of the exponential data or quantiles and along with the actual data, and if they match, that means the data is exponential in nature. So you can also apply some statistical tests. We are going to talk about these advanced hypothesis testing. These are called hypothesis testing, and we will see quite a lot of hypothesis testing in the advanced series on statistics. So by using those also, we can verify if the data is of exponential nature. The best is the domain knowledge. make sure we have someone on the team who understands the data and a domain, and that way we can verify and validate much quicker. Okay, next one is Winsorizing method. Winsorizing is a data processing technique to eliminate the extreme values. So if you have extreme values, you can map it to slightly lower value or something which again requires domain understanding. It cannot be arbitrarily changed to a lower value. For example, here, let's say the data is 20,000, 30,000, 35,000, 40,000. These are typical values in the data column. And some of the values are very high here. So with domain knowledge or consulting domain expert, we can substitute this 1 million with something like capped transformation, something like that. And this is called Winsorized mean. So when do we use Winsorized mean? It is useful when you want to reduce the impact of outliers without removing them completely from the data set. So Winsorization can alter the data distribution, and the application of Winsorizing or Winsorization should be based on the domain knowledge and the project goals. So process to calculate Winsorize mean, identify the certain percentages, let's say 5% of the both the lower and the upper tails of the distribution. If you feel you have extreme values at both ends, then decide either some percentage of it to be the target for replacing. So replace those values below the lower percentile with the value at the lower percentile. So that means something like hard fix. And the same way for the upper value, you can also choose to replace that with something like capped outlier. And then after that, you compute the mean here. All right, so that's pretty much I have in terms of central measures. This is quite simple. I'm not really going to show any Python code for these. These are readily available in NumPy and pandas, yeah, and you can apply those functions. Pretty easy. I mean, it's like one-liner. So in the next topic, we will talk about dispersion, which is like another characteristics or understanding the data characteristics using the spread of data. So we'll see you in the next lecture.